Okay, we can start. So, good morning and good evening to everybody. Welcome to this P4 Developer Day session. So, in today's session, Diedrich, PhD at KTH, is going to present his work called HOL4P4. Thank you, Diedrich, to join the P4 Developer Days, and the floor is yours.
Okay, so hello everyone. I'm Didrik and I'm an industry PhD student working at Saab and at KTH in Sweden. And I'm going to talk about HOL4P4, a formal semantics of P4 and some tools that we have built on top of it. And that's a lot of material to cover, which I've tried to compress into this half-hour presentation. First, a quick overview of the talk, so you know what to expect. I will assume that you, the listener, knows everything about P4, but nothing about formal verification. Therefore, I will start with an introduction, an executive overview with the main takeaways. And then I will present the HOL4P4 formalization and its set of tools from a practical perspective. And after you know a thing or two about HOL4P4, I will make a few comparisons to related work. And finally, I will talk about what you can maybe expect to see from HOL4P4 in the future, after which we conclude the talk. So, formal verification, what is it? The dictionary definition of verification, proving or checking that something exists, is true or is correct. The most intuitive and obvious way to check whether something is true is, of course, to test it. Writing unit tests, which most of you are maybe familiar with, is of course one of the most common and lowest threshold practices for ensuring your code behaves just like you want it to. Problem with testing is that exhaustive testing of all possible inputs to provide some kind of guarantee about the effect of the program quite quickly becomes infeasible. This is in contrast to the world of mathematics, where induction proofs can be used to prove properties about large or even infinite sets. Formal verification, then, on the other hand, in contrast to testing, can reason exhaustively about all possible executions by abstracting many concrete traces into a single symbolic execution trace. So this means that you can actually prove the absence of bugs with respect to your formal model. And this is especially important for example, non-reproducible behavior that could be introduced by concurrency phenomena, for example. So, formal proof depends on a formal model upon which the proof is stated. And in case of a program, the formal model would typically be then the semantics of the program language in question. And of course, we repeat that the property proved using formal verification always relies on the validity of the formal model used. So from a practical perspective, formal verification could be required by for the highest assurance certification levels, like in the common criteria framework, for example. And compared to testing, building the necessary formal models and tools for formal verification is a much larger initial investment, whereas you can begin writing tests pretty much immediately. But of course, if full automation in the formal verification tool is achieved, then the overall time investment, of course, will approach that of testing as you apply your verification tool to more and more programs, and this initial investment costs shrinks, relatively speaking. And maybe you can even avoid some bureaucracy in certification procedures if the trustworthiness of the verification tool is established once and for all, but this may be optimistic, of course. So the skeptical and critically minded audience is maybe thinking about an issue with this right now. That formal verification can never replace testing completely, since what is it that guarantees the correctness of the formal model? You can't just make up a formal model and then claim that this has some connection with reality. So accordingly, you must use testing to check that your formal model agrees with the real behavior. For example, that there is an input-output agreement between a P4 semantics plus a Tofino platform model with the program running on the real hardware. And this process is called validation. Validating actual systems against formal models is great for both language designers and hardware designers, since this makes it easier to debug and identify the exact discrepancies between formal descriptions and actual behavior. So I now invite you to consider, what is a theorem? The dictionary definition states a theorem is a statement that has been proved to be true. So, for example, a property of a program in this context. Okay, but what is a proof then? And we may loosely and informally think of proofs as something that convinces you of the truth of a statement, like a logical argument written down by a professor on a chalkboard. But let's try to be a bit more precise here. So in order to have reasoning, you need to start out with a logic, formal rules and axioms. And these rules and axioms, fewer than 2 dozen, a slightly different number depending on which exact flavor of logic you prefer, then constitute a foundation on which you can formalize and define the entirety of known mathematics, well, the mathematics that we use in practice anyway, without introducing any new axioms or rules. So we could therefore consider a proof something like a tree-like data structure, where the leaves are axioms and the non-leaf nodes are inference rules. And the task of proving a theorem is then the task of constructing its proof tree, and the task of checking whether a proof is correct is the task of ensuring that the proof tree was validly constructed. So the main goal of a type of tool called an interactive theorem prover is to prevent the user from proving theorems that are not true. And the previous explanation gives a simplified intuition of how this could be done, by ensuring that some data structure representing the theorem has a valid shape. In practice, the story is a little bit more complex, and things works quite differently for different theorem provers. The ITP, the interactive theorem prover used for this project, HOL4, uses the so-called LCF style approach, where theorem validity is guaranteed by encapsulation of the theorem data type. And encapsulation here is the same concept we know from object-oriented programming, meaning that the access to the data of an object is restricted to certain methods of the object. And then, of course, you use these primitive methods to define larger and more sophisticated methods in turn that are used to automate reasoning inside the ITP. And here we can make an interesting observation. When writing a regular analysis tool, the trusted computing base, the amount of code we need to trust in order to trust the correctness of the result, increases with every line we write in the analysis tool. But when we write a tool whose result is a proof of a property, the trusted computing base can actually stay constant if we keep the size of the formal model constant, that is. So we only need to trust the specific mechanism that ensures the validity of the proof, whether we rely on some encapsulation scheme or a post hoc proof checker. The size of this mechanism can be constant. And this, of course, is an increasingly important property as the size of analysis tools grow. And in addition, this creates a powerful and unique synergy with artificial intelligence. So writing proofs in the future could be effectively outsourced to AI agent, completely mitigating all the usual reliability issues that come with AI-generated code, since we know that the theorem prover can only always admit valid proofs. A phrase differently could say that if we submit to the strictest and most trustworthy mechanism of preventing bogus proofs, we can, in some sense, loosen up the methods we use to come up with the proofs, since we know only valid proofs will pass. So that's interesting, I think. But to round up, also a few quick notes about the practicalities of working with an interactive theorem prover. And while the main goal of the ITP usage is to ensure the correctness of the results, as I mentioned previously, they do, of course, also offer some general purpose and domain-specific proof automation that helps you to reason a lot faster than you would have done with pen and paper. Having to construct these ITP proofs can be very, very time-consuming. And a very major consideration when evaluating ITP works is the degree of automation of the end product or tool. So ideally, in my view, it's feasible that an end user of a software verification tool that's ITP-based has maybe no ITP or needs no ITP experience themselves at all. And automation is such a critical aspect when programming with ITPs. In my estimation, sometimes there can be as much as an order of magnitude more work involved when making a proof-producing tool compared to the same non-proof-producing one, often consisting of very tedious and repetitive proofs. So this really highlights the need to automate things, as well as fine-tuning these automated reasoning mechanisms to avoid inefficient or infeasible queries. And another important thing to keep in mind is that it's a bit wrong to value these ITP-based tools based on how many bugs in programs they have found or something like that. So as things are, for any category of bug you could identify, you could often easily be able to make a much faster non-proof producing bug finding tool. So the weakness of such a tool being, of course, that you don't have any basis really to reason about the absence of bugs. So the use case of ITP is the high assurance of correct behavior with respect to a formal model rather than catching individual bugs. But sadly, of course, verified software running as it should doesn't generate as many news headlines as these exciting bugs and vulnerabilities found in poorly written software do. So then things become as they are. So with those preliminaries noted, we're now ready to discuss HOL4P4. So in a single sentence, HOL4P4 can be described as a formalization of P4 made in the interactive theorem prover HOL4. And this has a number of components. So first, there's HOL4P4's internal representation of the P4 language, the syntax that is, as a slightly more minimalist version of P4. And the priority here is for verification and proof engineering. So this should be a minimal representation, which is balanced against the needs to have a legible representation, a clear connection to the surface syntax of P4. And real standard P4 programs can, of course, be imported into HOL4P4, usually without any modifications, using HOL4P4's import tool. And the priority here was to have the import tool do as much as possible of the work inside HOL4, which would in theory then allow to prove a meta theory regarding this import mechanism later. And finally, the semantics. So the goal of the HOL4P4 semantics is to, in the end, be able to run or simulate P4 programs inside the theorem prover. And the priority here is for the semantics to be simple and let's say, with a certain separation of concerns that enables proving a formal meta theory about it and the construction of further verification tools. Mainly here we had the symbolic executor in mind. And with regard to the meta theory, we have formally proved that semantics has a few very desirable characteristics like subject reduction and type preservation. And for more details on all of this, you can just watch the UPSLA presentation from last year on these topics. So just search for HOL4P4 UPSLA on YouTube and you can find it. I will only go over these things briefly in this presentation. So to be clear, these first 4 points by themselves are not really the end goal though. So it's at the point when you have all of these that you enable growing an ecosystem of tools and reaping the rewards of this entire effort. So built on top of HOL4P4, there exists multiple tools. For example, a symbolic executor and a verified compilation pathway to a software switch with more tools currently in the works. So let's then briefly take a look at these components then of HOL4P4 to understand how these design choices that we made facilitate the construction of such a toolbox. So let's take a brief look at the syntax and specifically now the HOL4P4 expressions. This is just copy-pasted from the UPSLA paper. Values, variables are the standard ones from P4, and all the standard arithmetic operations, the unary and binary ones are there. So as you can see, some things are also absent. There's no type instantiation or costs to named types. As much as possible that can be handled statically, that can be computed statically, is handled during the import stage by the import tool. And some other things like tuples and enumeration types can be desugared in some sense and represented as structs instead. However, there's no conditional operator, the if-then-else expression, as you might see, and no header stacks or header unions. But these could all be added pretty easily to the formalization. And next, the statements. So the top row here, also from the UPSLA paper, are all standard statements like the empty statement, assignment, conditional, return, sequences of statements, then the transition statement that's found in P4 parsers. So the apply statement is the first interesting one that sticks out from a design perspective. So note that unlike the standard P4 table application, this holds the list of keys being reduced or evaluated, maybe you could say. So it's important to connect back to the expressions here. So note that in the expression syntax, actually, there was no mechanism for table application. So indeed, all the table applications that do occur inside the expressions in P4 programs are desugared by the import tool into apply statements, and then with all the appropriate other adjustments to enable looking at hit and miss bits and so on. So this is actually highly intentional, because if we did have an apply expression, then this would need to access the architectural states where the table configurations can be found. But if we don't have this expression, then that totally eliminates that need from the entire expression semantics, which is very nice. So then we can keep this architectural state in the statement semantics and out of the expression semantics. And similarly, there's no function call on a statement level. So method calls, function calls that occur on a statement level in a regular P4 program are desugared again into an assignment of a function call expression to a special null L value that just discards the return value. And removing such duplication greatly simplifies the practical work done inside the interactive theorem prover. So the next interesting addition here is this black square. Maybe a black box is a better intuition, since this represents the semantics of an extern function. And note that this doesn't hold any arguments and is separate from calling the extern, which is done on the expression level, as I explained before. So call to extern functions reuses the regular function call, and the function body then of the called extern function will consist only of this black square, which in a single step of the semantics applies the effect of the extern. This is structured in this way because the same mechanisms then that use the P4's copy in, copy out calling conventions to restrict the side effects of functions, of course, we want to reuse them to similarly restrict the side effects of externs. And you could also observe that while this black square doesn't tell us which extern is being applied, it doesn't hold any information at all. Inside the semantics, the name of the current function being reduced is always clear, so that's easily accessible that way. And then we have just a block statement, the one with the braces there, which contains declarations of local variables also, the names denoted by the x's and the types by the taus, which are discarded when the block is finished. So what are we missing here on the statement level? So there's a switch statement, which can be fairly straightforwardly desugared by the import rule. And there's no exit statement. So why is that? Actually, in my view, the exit statement is a fairly interesting part of the P4 semantics. Also, it's not very easy in general, I think, to desugar it to something else in general. And some time ago, we actually sketched the addition of the exit statement to the semantics, but just never got around to doing it. So that's just another thing that's in the pipeline. And the HOL4P4 semantics has a clear and hierarchical organization where each layer above the expression semantics only is defined in terms of the layer below. And if you look at these 4 layers, then it should be noted that separating out an explicit architecture level semantics allows for more code reuse when implementing new architectures. And all of these levels are completely agnostic with regard to architectures. There's no specific semantics for some specific architecture, but rather different architecture are implemented in terms of different functions and different parameters in the static environment of the semantics. So let's take a look at the top level HOL4P4 state. And this state consists of IO bar, the list of incoming and outgoing packets and their respective ports. Alpha, which signifies architectural states, all of the architecture dependent stuff like extern data, tables, and so on. A block index I, which indicates which block we're currently in the pipeline, and gamma G, which contains the global variables. And then we have the frame stack phi bar. And this is a stack of a call stack, you could think of it as, consisting of function frames, which contain a tuple of the function names, mappings between local variables and their values, and the current function body being reduced, the statement, current statement being reduced. So notably, these local variables are not implemented like pointers to a heap, but mapped directly to their values and held in this part of phi bar that correspond to the respective function scope. So this we call a heapless semantics in contrast to the existing semantics at the time that this was originally formulated, specifically Petra. So what we mean with this heapless style, to be extra clear, is that all variable names map directly to their values. So in heap-based models, there's always an intermediate layer of memory locations, But since P4 lacks pointers, this additional layer is largely unnecessary. Furthermore, it's cumbersome since you can't just disregard the unused part of it without justification. You may also need to garbage collect this somehow. And in theory, this allows for aliasing, which can be a source of complications, of course. So with our frame-based approach, we always ensure that the view of variables is minimal and we don't have to deal with all of these issues. So moving down from the top level, down the hierarchy of semantics, at statement level, you don't have IO bar and I, just other components. And then finally, at the expression level, the only possible side effect, if you might recall the syntax for expressions, there's a function calls. The only possible side effect is a new frame being pushed onto this phi bar stack. And the rest is just reduction of the local reduction of the expression. And this separation of concerns is really neat and tidy from a theorem proving point of view. So keeping the state minimal for the respective level of semantics helps performance-wise with proof automation and also makes it easier to prove the meta theory. So that's it from a high-level perspective of the semantics. So let's just briefly discuss how this import tool is constructed. So it uses an external part of Petra to just, this will of course type check the P4 program, but it's really the parsing of the P4 program that we're interested in, and the export to JSON format, which is then parsed to a HOL4 term by our HOL4 JSON parser, and finally transformed to the HOL4P4 format by the last stage of this import tool, which also does quite a bit of inlining and desugaring to represent P4 programs in this concise HOL4P4 syntax. And we also have a type system, which we use to prove in HOL4 two nice properties of the semantics, type preservation and progress. So type preservation states that if the initial state ST is well typed, and if ST is reduced to ST prime in the environment big E, then ST prime must also be well typed with respect to the same. So the progress property states that if the initial state is well typed, then either there must exist an ST prime, so that ST goes to this ST prime, or ST is indeed a final state. So with that said, let's take a look at the symbolic executor. What can you do with the symbolic executor then? So the symbolic executor is in theory not restricted to any class of functional properties and proves properties roughly of the form: if the precondition P holds, then the code successfully executes and the postcondition Q holds afterward. Glossing over the details of how exactly to encode such properties in HOL4, this could, for example, be that if ingress port is N and source MAC address is A, where you expect a certain shape of the input packet, then egress port is M. So these assumptions in P may refer to bits of incoming packets or to tables or to external behavior or anything really. P and Q are general HOL4 predicates, not restricted in any way, and may include quantifiers and everything you want. However, note that the proof automation inside the symbolic executor might, of course, not be able to cope with arbitrarily complex properties, meaning you would need to supply some tailor-made reasoning mechanisms to the final stage of the symbolic execution when you try to prove the postcondition of such a functional property, or maybe even handle it manually. So the symbolic executor can over-approximate automatically externs and tables, meaning that table configurations don't need to be known beforehand. You can start out with some assumptions on these configurations, but you don't need to know the concrete configuration. And similarly for externs, this is the case. So their effects can be automatically over-approximated so that if, for example, you're computing a checksum, the symbolic executor would just say, well, there exists bits such that the checksum computes the result of those bits. And then you just move forward with the proof from there. And hopefully, of course, the property that you want to prove is independent on the exact values of these bits. But if it is, then of course, the symbolic executor will also exhaustively consider those possibilities. And this is 100% fully proof producing. So the correctness of these results doesn't depend on any external oracles or anything like that. So now say that you would want to apply the symbolic executor to the program. What do you need to do, practically speaking? So assuming that you've installed HOL4P4, you would start by running a shell script in the import tool directory to import the P4 program you would want to analyze. This would give you a HOL4 script file suffixed with script.sml, which contains the HOL4P4 representation of the program, together with some boilerplate code that will just run the symbolic executor with some default parameters. So the next step, which is a slightly manual, of course, is to encode the pre and post conditions that constitute this functional property you want to prove. And if it's just a simple example program, you're done. But if this shouldn't work out right, you would get some kind of error message. And quite possibly that the post condition couldn't be proved from the symbolic execution results, for example. So if this is the case, you would need to supply some more powerful or custom reasoning mechanism for the symbolic executor to apply at this final stage. And the most serious drawback, I would say here, is that as programs go larger and larger and into thousands lines of code, you would need to, for performance, pure performance reasons, to break up the proof into multiple smaller proofs and add mid conditions in between these. And the natural strategy here for P4 is, of course, to split this up for the individual programmable blocks, which, of course, means also that combining these results then is easy. You may want to do this in a more fine-grained way and prove separate contracts for large tables, for example, or complex tables. It's a bit more fiddly to do this type of composition inside blocks. So for the simple use cases, all of these initial steps up to 4 or maybe even 5 could be almost completely automated. You just supply the P4 program and the pre and post condition that you want to prove for your functional property, that you want to use for the functional property. And however, for the larger programs, it's a bit fiddly to split this up. So this would be hard to automate. And what did we apply this to? So, well, there's a small test suite for sanity checking and simple properties, and there's a very rudimentary IPsec P4 program. And of course, there's some larger industry applications that are completely internal to solve. But a few of these examples are described in the paper that describes the symbolic executor. So please read that if you're more interested. And I don't think there's any recorded presentation there. The performance is still the aspect of the symbolic executor that could be improved further. So yeah, here are some examples of rough estimates of the performance of the symbolic executor. Can of course vary a lot, but so without radically changing the current approach, I would estimate that it's definitely not possible to improve these numbers by more than cutting them in 10 or something like that, you could maybe cut them in half or in 3, something like that, but absolutely not more than that. So that seems to be a quite fundamental limitation. And you can, of course, speed this up always by adding more and more annotation and splitting things up manually and so on. But that's also not desirable. You want this to be as automatic as possible, really, for the sanity of the end user of the tool. So another recent project that makes use of the KML verified compiler, and that's a part of the HOL4, wider HOL4 ecosystem, is the project to obtain a verified P4 interpreter that you can then run as a software switch with some formal guarantees that the P4 program is interpreted correctly according to the HOL4P4 semantics then. And this we have affectionately named HOL4P4.exe. And this can be run currently on a standard x86 Linux platform, and it's very easy to integrate this with Mininet, for example. And this work is still very fresh, so the paper is not out yet, but should be very soon, I think, viewable. And the work is still isn't merged into the main branch of the repository, but will be very soon. And since KML also targets RISC-V and ARMv8, I think it would be very simple to get a verified P4 software switch running on those platforms. We just didn't try it yet. So how would you use this then? So setting up the HOL4P4.exe is mostly completely automatic. So you just run a shell script that imports the P4 program, same as before, with some different flag to signify that you want to use this with software switch instead. Then modify the initial state to contain the table configuration you want. If you didn't already hard code this into the P4 program, then you don't need to do anything here. Then run another script that compiles the HOL4 theories and runs the KML compiler after that, which finally yields a binary. And this also takes some flags that decide on a map between P4 port numbers and raw sockets as a command line argument. But then after that, the software switch is immediately deployable. So what kind of experiments did we do with this? So we've experimented with compiling a few programs using hard-coded table configurations. And the largest example is Google Fabric Border Router P4 program, just below 3,000 lines of code, something like that. And then we also applied this to the familiar VSS example from the specification, ported to V1 model. And of course, some smaller examples for testing and micro benchmarking. This is all in the upcoming paper, which also contains a lot more detailed benchmarks. The gist of it is that HOL4P4.exe is slower than BMB2, but significantly faster than the software switch version of Petra that was demonstrated at CAV a few years ago at a tutorial session. That is after we disabled debug messages and etc. in the P4 source code that was slowing things down a little bit. Even then, HOL4P4.exe is a lot faster. So the VSS example ported, as an example of the performance ported to V1 model, has about 20 megabit per second throughput and a latency of just above 1 millisecond. And the Google Fabric Border Router program has a 2 megabit per second throughput and 16 millisecond latency. Of course, this is just presenting one of the paths through the program. So while this is already a promising proof of concept for certain high assurance settings, the good news is that some additional experiments we did show that I think that An approach using direct compilation here could actually even beat BMV2 in performance. So for very small programs, we have experimented with a technique that sort of extracts the notational semantics of the program by using the symbolic executor as capturing what's actually being computed. And by compiling this result as a function, you get something that's just a bit faster than BMV2. So, I mean, not better than half the latency or something like that, but just a healthy bit faster. So the issue is really the interpretation approach here, not really the KKML compiler or the wrapper code handling the raw socket interaction or something like that. And so if this would scale to larger programs, then these direct compilation techniques could maybe achieve a throughput of 100 megabits or 200 megabits or something like that for VSS-sized programs. So as you might recall, the embellishing word ecosystem was used in the presentation description, and there wouldn't be any proper ecosystem if the constituents didn't have some kind of mutualist relationship where they actually benefit from each other's existence. So let's take a look at this. So most obviously, the verified compiler can preserve functional guarantees from the symbolic executor. And the mechanism behind this is quite straightforward. The verified compiler compiles the exact same function that the symbolic executor proves properties about. So if you only had one of these tools, then the trust situation wouldn't look as good. So you could maybe prove properties about the program that gets totally mangled by a compiler, or you could verifiably compile a program whose correctness was only ensured by testing, which is not as good as this combination. And secondly, which is a bit more experimental, but the symbolic executor could be used for an alternative compilation pathway or to optimize programs, parts of programs before compilation. So yeah, I already went through the interpretation versus direct compilation before, but the output of this symbolic executor can be used to reconstruct or somehow obtain the denotational semantics of a function with the same input-output behavior as in terms of packets as the P4 program, which abstracts away all the busy work when interpreting the P4 program. But of course, using this symbolic executor can be very slow for large programs and require some manual labor to split things up if you have programs of, I don't know, 5,000 lines of code, something like that. So this approach wouldn't scale very good to larger programs, perhaps. So with all of that about HOL4P4 sorted, I just wanted to mention some of the other similar work that has been done. And firstly, Petra, of course, is the first formalization of P4 and was originally written in OCaml and later written using the theorem prover ROC. And most notably, in comparison to HOL4P4, it's a heap-based semantics that more exactly mirrors the surface syntax of the P4 language. And the original paper presented no proof-producing verification tool, but some of the authors later made some tools, like the Leapfrog tool for parser verification and P4cub, which is a formalization or alternative intermediate representation, an alternative to the Petra semantics in a style that's a bit more closer to HOL4P4. And secondly, there's verifiable P4, a formalization and tool originally presented at ITP a few years ago, which at the time it was presented seemed to have a more limited scope than HOL4P4, but has since been elaborated on, and there's multiple theses and a preprint from last year that describes a verification toolbox that's meant for verification of complete P4 programs. So this is similar in capability and scope to the HOL4P4 symbolic executor. I don't know a lot of details about the performance or the exact degree of automation, but they seem to have a lot of nice and very interesting case studies involving this toolbox where they combine different verification techniques. And as far as I know, verifiable P4 doesn't have any means of verified compilation yet, but I think large parts of such a solution would already exist in the larger ROC ecosystem. So compared to other work, generally I would say that HOL4P4 is mainly distinguished by not being concerned with what a well-formed P4 program is. So that's outsourced pretty much entirely to Petra by us. So by the time that we get something out of Petra, we consider this to be a well-formed P4 program with no further questions asked. And then we, of course, have an internal notion of well-formedness for our own HOL4P4 syntax. That's a bit different. And other work also has a very clear ambition to participate in language design, and the formalizations correspond more directly to the surface level appearance of standard P4. So our goal then from the start has been to facilitate proving meta theory, making verification tools, and that's a bit of a different focus. Also, we are focused on concurrency, as you can read about in the UPSLA paper, but this really hasn't come into play much for general purpose tools. So let's just look at what we're working on right now, and then we'll conclude the presentation. So Pancake is a C-like systems language which reuses some of the KML compiler infrastructure that's been famously used to write and verify stuff related to Lion's OS, the operating system built for the SEL4 microkernel, like a NIC driver, for example. And the current HOL4P4.exe setup, where the verified software switch is implemented as an interpreter, is not ideal for performance, as I mentioned, similar to how interpreted languages like Python are slower than compiled languages like C. And directly compiling from HOL4P4 to Pancake is an interesting avenue to speed things up. And there's actually an ad for a master thesis related to this out already, so this is ongoing work. And I should add that also in the HOL4 world, there exists work doing verified compilation to FPGA hardware. And obviously, verified compilation from HOL4P4 to FPGA would also be a complete game changer for performance, but perhaps a bit more difficult to put together. And secondly, we have some collaborators who formalized control plane functionality. So the HOL4P4 semantics has been designed to enable reasoning about interleaving between parallel pipelines, as we show in the UPSLA paper, but also between the control plane and the data plane. And the formal control plane model could be combined with the HOL4P4 model to prove properties about, for example, global properties of a network while updating control plane configurations. And the HOL4P4 switch could, of course, also be extended with some verified functionality to dynamically update the tables based on Mac learning, for example. So in conclusion, I hope this presentation has been interesting. I hope you've learned something. And specifically, I hope you've learned the principles behind using interactive theorem provers to build verification tools, how the HOL4P4 symbolic executor can be used, how the HOL4P4 software switch works, and how to compare HOL4P4 to other efforts. And if you feel that you didn't learn some of these things, I'll be happy to take questions that perhaps can clarify the situation. Thanks for listening.
Thank you, Didrik, for the presentation. It was very interesting and super clear. Truly appreciate that. So I don't know if someone from the audience have a question for Didrik. So in the meanwhile, I have one. So in the previous P4 Developer Day session, P4 Spec Tech was presented. So how would you describe the similarities and the differences between your work and P4 SpecTech?
Yeah, that's a very good question, actually. So I think the two main differences is that we're working inside an interactive theorem prover. So we're interested in proving things formally, and all of our work is oriented around this. And I don't think that's currently part of the scope of the SpecTech project. Maybe it will be in the future, some capability of exporting to ITPs. And secondly, I think that SpecTech is very oriented towards language design and helping out with language design and so on. Whereas HOL4P4 is mainly concerned with construction of automatic verification tools, and not so much, I guess, providing rapid feedback or helping out with language design.
Okay, thank you for the answer. Yeah, Jae Yoon, you can give us your view about
yeah, that would be great.
SpecTech. Indeed, would be great.
Yeah, so thank you, David, for mentioning P4 SpecTech, and thank you, Diedrich, for the great presentation. It was very helpful to understand what HOL4P4 does. So and it's also about the previous question. It's true that we are not into verification of P4 for now, but maybe in the future we might want to generate some mechanized definition for interactive theorem provers as well. So thank you for mentioning. And I have two questions, so I may want to ask them one by one. So the first question is about the verification of P4 programs. What may be the properties you might want to prove about a P4 program? I was curious, like you mentioned several programs that you have verified, and what are the kind of the properties that are proven in the P4 program? Maybe just absence of a static typing box, or
no. They were all functional properties. So we're interested in verifying functional properties. But I think with regard to the examples in this symbolic executor paper, I mean, they were fairly trivial functional properties. So nothing super interesting, just some basic correspondence between maybe egress ports and table configurations and some part of the input packet playing into this and so on. So nothing super exciting, but basic correspondences between some aspects of the input packet headers and the table configurations and the final results. Yeah.
I see. Thank you. So I think it's super interesting because it does give a guarantee that the P4 program is working as intended. And the second question is a little bit technical. So it's more about the HOL4P4 mechanization itself. So in my own viewpoint of the lifetime of a P4 program, I think it goes through mainly three stages. So we first type check the P4 program, and then we would instantiate the the stateful elements in the P4 program statically, and then we would dynamically execute these stateful elements. And in the HOL4P4 mechanization, I can see the static type checking phase and also the dynamic execution phase. But I thought the instantiation phase was kind of missing. So in the architecture semantics, it kind of assumes that the objects were pre-allocated in the architecture itself. So I wondered how HOL4P4 is handling these static instantiation.
Yeah, So let me think about this here. So static instantiation, for example, you're referring to external objects that exist at the top level of the program?
Yes, at the top level, and also in P4, we can instantiate externs within a parser, within a control, and within parsers,
Yes,
we
of course,
can
of course.
the other
So,
parser.
so if there are objects, external objects that are instantiated at the top level, then those should be instantiated in the initial state when commencing verification. So when you symbolically execute how a symbolic packet goes through a P4 program, then in the initial state, as you said, using the word pre-allocation, this top level extern is already instantiated. However, if we have instantiation inside, say, a programmable block, then this will be allocated upon every encounter of this block. And then, depending on the program, the architecture in question or the external in question, there could be different conventions or mechanisms for deciding whether to have persistent data or not.
I see. Thank you for the answer.
Someone else have a question? Okay, I have another question. So, is there anything you would like to have done differently during the semantic design phase in retrospect? And if so, why?
Oh yeah, this is a good and interesting question that I could spend a lot of time talking about, I guess. But so one of the aspects is that, for example, I mentioned that the side effect, potential side effect of expression level reduction is that a new function frame is generated. And so I was thinking that maybe this should be performed actually at the statement level instead. I mean, the generation of the frame, so that the expression level semantics only passes the function name. Because then at the point of generating the new fresh scope, we have the architecture scope available. And it so happens that way after we had initially defined the semantics, we came up with means to generate a method to generate random bits or to over approximate uninitialized bits and so on. But in order to really work with this in a nice manner, we need to have some kind of, let's say, a tracker or a ticker to separate the individual, let's say, random bits, for example, or different uninitialized bits and so on. So this has become a bit of a mess, I guess. And also, of course, I think that maybe we should have added some slight bit more of the more obscure expressions and statements, I guess.
Okay, thank you for the answer. So someone else have question? I would say no. So this P4 session will be, P4 days developer session will be available on p4.org together with the slides. And thank you again, Diedrich, to join the P4 Developer Days and to give us your presentation about your works. It was very interesting. So the next appointment from the point of view of P4 Developer Days will be the 1st of October. And the title of the presentation is Enabling Portable and High Performance Smart NIC Programs with Alkali. And so hope to see you there and have a nice day.